Hello, welcome back to Intro to Cognitive Science. Today we're going to talk about levels of analysis. So far, we've been talking a lot about information processing at a few different levels, right? So, single bits being the smallest possible piece of information. The symbols of a Turing machine being a little bit more complex, right? So they had multiple possible values, right? Systems that actually can talk to one another, like Shardlu, they were able to pass information back and forth in these sort of patterns, these complex ways to be able to actually render a sentence into an instruction to its hands, quote, hands. Sorry, you can't see my double quote fingers. And the also more complex like mental imagery as information, the way that a computer stores and represents images, the way that we store and represent and change and manipulate images internally, that kind of stuff. So we've talked about information as this kind of broad thing, right? It can be a single bit or it can be an entire lush photograph, right? And so this brings us to the idea that we can talk about these various things at different levels of explanation. There's smaller amounts of information that move around in different ways that might compose a larger chunk of information. So think about this. Here's a simple thing. A turtle. We think about turtles as an animal, right? But if you think about a turtle, you can zoom in a bit. The turtle has a lot of subsystems to it, right? It has a shell. It has lungs and do they have gills? Actually, forget this. Either way, maybe they're amphibious or I don't know. But they have a variety of musculature, bones, brain, heart, all these moving independent things that all connect to one another. But those things are composed of a cellular structure, right? An individual cell has particular functions and pieces and different parts, right? And a heart is made up of a variety of different cells. Each individual cell is built of a whole variety of chemical processes that make the cell do the things that it does. And then further down, those chemical processes are dictated by physics, physics by math, blah, blah, all the way down, right? So each level of analysis, level of explanation that you talk about this turtle at, it addresses different questions. It has a different value contributed to the whole understanding of the turtle. Knowing how a turtle's heart works might help us understand how the turtle lives, right? And so this is getting to a big concept, big in many fields, but huge in cognitive science, bottom up and top down. Bottom up explanations and studies and theories are about if you study how, say, the cell works, it might help you figure out how the organ achieves its processes, right? So let's say the first biologist in the world, cells seem to react to light. Cool. So I wonder if the leaf is actually using light for something, right? Maybe the leaf is sensitive to light altogether. Versus top down, studying how the organs themselves function without necessarily knowing about the way the cells are working, we can ask a different question, but related to the same interchange between these two levels. Well, the leaf is definitely reacting to light. If I don't give this plant light, it dies. So must be something at the cellular level that is photosensitive, right? These are both two ways of approaching, given what you already know, approaching a different level of explanation. So if you know a lot about the leaf and the organism, you might be able to make some questions and assumptions about how the cells work. But if you know how the cells work, you might be able to ask questions, new questions about how the organ and organism work. So that's a big topic. This is a big theme that will pop up now and again because anytime you're dealing with complex systems, and believe me, the brain is one of the most complex we know about, you can address them from different levels of explanation, and bottom up and top down come in a lot. So, let's talk about Mar. Mar comes in and starts to split up this idea of, hey, we should come up with some terminology to figure out how to split up our understanding of the processes of cognition into these different levels. So the idea is, first poses the idea of levels of explanation generally, and then he poses one specific top-down model of cognitive levels, and then comes up with a, as full as he can make it, model of one specific cognitive process, early vision. And you'll see all that shortly. So, levels of cognitive science. Different disciplines are going to tackle different levels. So they're going to ask questions and use different techniques, right? An experimental psychologist might use human behavior as their chief currency. This is the things that they talk about are predicting behavior patterns, describing behavioral archetypes, and all that kind of stuff, right? Whereas neuroscience is going to talk about things all the way down to individual neurons and even neurobiology, all the way up through, groups of neurons and the networks and how network neuroscience works. Computer science and AI is going to talk about just the informational algorithms, whereas maybe information theory and computation talks about how do you turn that into hardware, right? So these are all they're all focused on the idea of the information processing world of, humans being biological versions of this, but computers being artificial versions. But they're all talking about different layers, different levels. So that's key. That's key to understanding how the interdisciplinarity of cognitive science comes to be, right? So you get questions and answers at different levels that all talk to each other. We've looked at some different levels so far. So Miller's magic number 7 was about these very basic information capacities, right? These small channels of neural activity that we think show, oh, there's only so much bandwidth on this bundle of neurons. He never really highlighted it, never really pinpointed where those lived, but that was the idea. Turing connected algorithms, so the actual moving around of symbolic information, to the higher level computational type things. So, hey, I know that I can do a not operation. Turing's algorithms in the Turing machine show, here's how you would do that to a string of symbols. We looked at Broadbent's model, or more accurately, we talked much more about Sherdlu, of this sort of connected systems. I guess Broadbent's was about a little bit about subsystems, but about more information attentional processing type stuff. But both of them, Broadbent and Sherdlu, talk about the interconnected subsystems, right? So information moving around, not just what's the capacity of the channel, but more at a higher level, how does the information move between different chunks of the system that's processing it? And then we also talked about imagery. So how is information itself coded into a substrate that can be, pulled back again? So the hard drive or the brain. Okay, that's just a sort of a grab bag, just to demonstrate that everything we've talked about so far does live in different kind of spaces in terms of what level of complexity of information we're talking about. So this is sort of Mar's goal. Mar wants to come in and say, hey, so any task we're thinking about, we're all talking about, again, remember that this is the long walk towards a more coherent field of cognitive science. So Mar sees, hey, everyone's talking about different things. Is there a unifying principle we can use to organize the field? Now, that's not to say that fit everything in a perfect, neat little box, but more, can we talk about one phenomenon, say the way that information moves around, right? and have bridges to the higher level and the lower level. So he's trying to combine them. And to do that, he comes up with 3 levels of information processing: computational, algorithmic, and implementation. Let's talk about them. So, computational analysis is sort of the high-level task of any cognitive system. What problem is the system trying to solve? What sorts of constraints are on that solution, right? We'll look through some examples here shortly. The algorithmic level is more about how you actually go about achieving those things, right? So how do you actually solve that task? Not just what is the task doing, but how does it achieve it, right? What are the steps involved? How do I transform the information from the inputs to the outputs of this particular computation, this particular process, right? And also, how are we actually encoding this information? Finally, at the bottom level of any of these analyses is how is this algorithm actually implemented in the real physical world, right? So if I was going to describe a process of how to pull up a piece of it, an image, a photo off of a hard disk, this is where we get into how exactly are the pixel data stored on the disk. How does that happen? How is that possible, right? And in the same vein, neurons, right? How can we use them to represent the information needed for the algorithms? And then how do those neurons and other neurons around them transform those representations into different shapes, right? So for language, how do I actually store the rules of the context-free grammars, and then a different set of neurons has to come in and transform them, right? And that's the implementation level. So here's Mars levels a little more just for reference, right? Just I threw it on the slide for reference. So what's the goal of whatever thing we're doing? That's the computational level. How can it be implemented? And then how is it actually physically realized? So let's look at some things that we've discussed. First, consider Shardloo. What was Shardloo as a process, as a whole system? What was its goal, right? What was its computational goal? It was attempting to capture language in a microworld, right? That's this sort of high-level understanding of what's going on, right? This is the encapsulation of all that. At the algorithmic level, it was a little more, we get a little more in depth. How does it achieve this, right? So it has various language processing units that work together to parse words, right? Parse out the meaning of words and the semantics and the syntax, and create this sort of meaningful understanding of its tiny world. The implementation, well, we can just leave that at it's a computer, right? A computer is quite capable of doing all of this. It moves the information around. It captures everything in ones and zeros. In fact, that's how it did its thing, right? It just displayed it on the monitor using those old school CRTs, right? So Shardloo, that's the multi-level analysis of Shardloo. Implementation is usually much more complex, right? We have to get into all the details and nitty-gritty, but the idea is that the computer is doing that for us, right? What about a Turing machine? Turing machine, what's its goal? Its goal, if you recall, was capture any possible function. Oy, okay. The process of any possible function, right? Not just one computation, but all computations. Its algorithmic analysis is basically the instructions from the machine table would tell it how to maneuver the information around on its tape, right? if it saw this, it would do this. If it was in this state, it would do this. That was all left on the algorithmic table, the machine table. Implementation was not specific, but it was possible. It was possible to make assuming non-infinite tape, of course, to make a Turing machine. In fact, people have done it. Like I said before, all modern computers are technically Turing complete, but this is also just people have made these for fun, showing, hey, I can make a system that will do this. Okay, let's do one blind. We'll describe each of these layers and try to figure out what is this thing, right? At the top layer, what is the computation? What is the function? What is the thing that it's trying to achieve? We'll push button cook food. Okay, that narrows it down. That's a lot of possible things, right? And that helps. That this is helping to illustrate that we can use many different things, many different algorithms and implementations to fulfill any given computation, right? The computation here is push button cook food. I can think of a few things, different various kinds of ovens. I have microwaves. I have a hot pot. I have rice cooker, something. Everybody's got a bunch of different things for push button cook food. Okay, so what's the algorithm that this particular thing uses? Convert cold food to warm food. Okay, we're still dealing with the inputs and outputs based on user inputs, using a process of heating using radiation at a distance. Okay, we're getting a little bit more information about this here. We're seeing more of how this particular thing does its job, right? Not totally sure yet, but we're narrowing in. What if we go one deeper to the actual implementation? Send energy through a magnetron to emit microwaves to excite the water molecules of consumable material inside a Faraday cage with an electronic timer that shuts off after, etc. A microwave. Okay. So I hope that helps you see how much more interesting these objects can be. But it also helps to illustrate that there are different levels of complexity that you can think about an everyday object had. So, cool. I hope this helps to illustrate the idea of this computational, algorithmic, and implementation layer discussion, these levels of analysis. Let's move on to how Marr used this to try to tackle, he tried to use this system, he tried to demonstrate this by saying, hey, what if I took this to something real, something that we already know humans do? He's talking about early vision. See, early, I'll explain that momentarily. So this is a pretty well-documented piece of the cognitive puzzle. Vision is nice to study because it's so obvious. It's in very clear channel. Well, I don't want to discount as though it's simple. It's not simple. It's just that it's easier to study these things in many ways because it's quite easy to stimulate the vision, cleanly stimulate vision in human eyeballs, and easier to observe a lot of what happens at the lower levels of the brain. So anyway, that Marr is attempting to apply his levels of analysis to the early visual system. So this is the system that takes light from the eyeballs and turns it into something, useful for the rest of the brain to use. So let's trace out the pattern, right? Here's a cross-section of the brain, and also the eyeballs are hooked up. Yeah, look a little freaky. Here we are. So we have light coming in from the world, right? We have the left and right visual field. It hits the retina in the eye, at the back of the eyeball. Carries itself along the optical nerves. It doesn't carry itself, the neurons carry it, but it moves along the optical nerves, and then it hits the occipital cortex, occipital lobe at the back of the brain, and then from there it processes out to the rest of the brain, and then you're able to make decisions and actions and all that. Marr's approach to saying, hey, I want to zoom into one step of this process and figure out how must some of these algorithms work? He's looking at the steps between the optical nerves and the occipital cortex. So, Mars early visual system. It's a couple of key concepts from empirical work. We'll talk a little about that. In medical settings, this happens quite often. So, an important idea in all of vision is that the information that comes in is getting changed into different patterns, different shapes, and well, I don't want to use the word shapes, different forms, right? Different representations as it moves throughout the brain, right? And that information seems to be abstracted a little bit, right? You can see more than just exactly what's on your retina. We are processing it in some other way that gives us a little bit more information than what is just the pattern of dots of light. So, from the experimental side, there's a lot of evidence from people with brain damage, especially in the parietal lobe. So the parietal lobe has a lot of associative and spatial stuff going on. So trying to make sense of the 3D spatial relationships in the world out of the visual patterns you get on your eyeballs. So here's an interesting thing. In patients who had right hemisphere damage, they were able to identify objects, but they couldn't solve spatial problems related to those objects. So they could say, I know that that's a hammer, but they couldn't figure out how to use it. Whereas if the left hemisphere was damaged in the same lobe, they could understand the spatial properties, but they couldn't name or label the objects. The idea here being that the visual systems seem to be passing information along to at least these other recognition systems, but also, to the 3D parietal spatial systems. The same information, the same visual pattern that the eyeballs are receiving, in some people, fails to activate these downstream elements, right? Making it so that it's hard for people with damage in certain areas to identify objects, and hard for people with damage in the other areas to do spatial tasks involving them. So this is interesting. This is suggesting that there is a pathway, multiple pathways even, more than one here, that converts visual information into some other different useful form. So there's also some theoretical evidence at this higher level of just, task analysis, right, or overall analysis of your recognition abilities, for example. They don't depend heavily on the exact retinal pattern you're experiencing, right? There's something else activating in your brain. There's something at a higher level that multiple versions of the same visual pattern show. For example, I don't have to be looking directly at you for you to see that, oh, that's that guy's face. In fact, I can grow a super long beard, shave my head, and you would probably still recognize me. Now, faces are kind of weirdly powerful things in human brains, but you get the idea, I hope, that you don't need the same exact visual pattern to make sense of a thing as sort of the same object, right? For example, look at this dog. This dog is activating a certain amount of visual information on your retina, right? It's stimulating a certain number in a certain pattern of your neurons on your retina, the receptors on your retina, and you see a dog. If I do this, you don't think, oh God, that's a different visual pattern. That dog is a different dog. That's a tiny dog. No, that dog got further away. The visual pattern changed, but you've made sense of it. You've told a story about it. You've processed the information to say, oh, the distance value has changed. What about now? The dog is closer. The dog is very close to you now. But it's a different visual pattern. You are not doing everything based on a static image processing power. You are abstracting some information about this dog that allows you to maintain your understanding of it. How about now? That's the same dog, he's just upside down. How about now? That dog is fine. You assume that that dog is behind this wall, right? You don't think, oh God, he's showing me a dog's head cut off, right? That would not make a lot of sense, but it just also doesn't, that's not the assumption. That's not how the visual system is automatically going to parse this. So you are using a variety of abstractions to say, okay, the exact thing I am seeing right now is potentially related to all these other versions I've seen. So your recognition abilities don't depend exactly on one specific retinal pattern, right? Orientation can change. An upside down chair is still a chair. The distance, it's not larger just because it's closer to me, right? Occlusion, it's not broken just because I can't see all of it right now, right? We are representing it a little more abstractly than just the light that hits my eyeballs. We have some kind of internal concept of the object that we can compare it to. So, if Mar wants to tackle this little chunk of the visual system, how do we do it? Here's what Mar proposes. The visual system's goal is to create some sort of 3D representation of the world and all the objects in the world, just the outside scene. And then it needs to be able to pass that information on to other brain systems so that people with damage in certain regions would be able to process things differently than those without the damage, right? And then it also needs to do this other step to make the representation object-centric. That's interesting. The idea is that the representation has nothing to do with me or where I'm at. It has to do everything with what are the spatial relationships of the object itself, right? So the dog has its own properties. It has its own shape. And I need to make this 3D representation that has nothing to do with my exact position in the world, but more to do with the dog's shape in the world. So, that's a lot to ask. Oof, that's a lot. And he knew this. This is a lot. But we've broken down a very complex thing into a set of processes that can now be explicated. We can detail them. So that's where we zoomed down a level from this top level. His requirements were, again, recap it quickly, 3D representation that can be moved around the brain and is object-centric, right? It's not dependent on my viewport. It's dependent on the object itself. Okay, so how do we make a set of algorithms that can do this? Well, how would any system, right? That's the algorithmic question. How would anything achieve this? How would anything carry out this 3D representation task? The input must be the light on the retina, right? We already know that. And we've already described the output as well. The 3D representation that we're going to use later in other parts of the brain. Use it to identify it, but also use it to understand how to solve problems with it. So what sort of information can we get out of the light on the retina that we can then transform through, algorithmic steps into a 3D representation that can be used later in other abstract ways? Interesting. So, this is where he starts to dig into the meat of this question. There's a lot of stuff available in visual information that they are hallmarks of these kinds of 3D patterns, right? You can get a lot of information about the luminance, the reflectance, the angles, the colors, the shades, all that kind of stuff of just what's right there in the image, right? So we need to identify what are the very specific processes that you need to turn light dots into structure. A pattern of light dots into a 3D structure. I put this box up here, just a generic box, because you know everything about that box. I've just shown you a pattern of light dots, but you know what material it's made of. You know how roughly deep it is. You don't know the exact scale. There's no banana. There's no person's hands. But you know roughly what this box is like. You could probably build it yourself just from this image. So the question is, how the heck is your brain doing this? So, what Mar details is this idea of representational primitives. So primitives are what is the most basic information available. And again, the information on the retina, intensity value is pretty big. So neighboring changes in the value could suggest boundaries, and boundaries could suggest other important things. Like, this is a surface. This is a wall. This is the inside surface of the box. This surface is at a 90-degree angle. These kinds of very important things, right? So, these are called zero crossings. So any sudden change in this primitive value, the luminance, the intensity of the image in front of me, a sudden change suggests there is structure there. So, zero crossings. It's about these extreme changes in visual intensity that suggest there is a meaningful difference between one thing and another thing, typically surfaces, right? So these are some zero crossings of the leaf. I think the raw leaf is the upper left. You do a couple of layers of zero crossings, you get these sort of, oh, I'm seeing that there's like some venous looking, veiny structures, right? Those are meaningful structures for how the leaf works. How about this? What is this object? Right off the bat, you're probably thinking, I don't know, like rhombus, sideways diamond. Is that a rupee? I don't know. What about now? It's a box. Duh. Instantly, your brain filled in the details that this, because there are these sharp changes between the luminance and even the color of these different surfaces, this now looks to me to be a box. In fact, it might even look like a box that is all the same color, even though I'm getting totally different color values from each of its surfaces. Your brain is doing something with this zero crossing information. Going back to nothing. Going forward to the pattern, to the structure. I can dissolve it too by showing you that, oops, these are just a bunch of different distinct shapes that I put together in Keynote to make it work. But okay, put it back together. And the illusion comes right back, right? You almost have no choice but to see this as a box because there is no zero crossing information anywhere else on it. So, sorry, what I mean is on the planes of those, there's no zero crossings on these broken shapes, right? So even if they're broken shapes, when they're together, there's no zero crossing. You cannot pull them apart anymore. They just are a surface. So, step one in Mars levels here relies on these zero crossings. So it creates what is called, or suggests that our brains create what is called a primal sketch, right? So the idea is to go through whatever the visual pattern that you're looking at is and identify the intensity changes in that visual pattern, right? So the zero crossings. Find where the crossings are. The primitives here are zero crossings and these virtual lines and then groups of lines can be combined to create a 2.5D sketch. That's an interesting kind of weird thought. What's going on in this? So the next step, we've got all these lines that we've detected using zero crossings, right? We've split the image up into its line segments. Well, now we can start to figure some things out. What things in this image are surfaces and which things are not surfaces? Which things are edges? Which things are one surface versus a different surface? What orientations are objects in? You can see this thing on the right here. We have this sort of, okay, this is my visual pattern. I see this kind of cake-looking layered cylinder thing. I get that it's sort of, these surfaces are facing different directions. The cylinder is facing kind of outward all directions, depending on where. The top is flat. I kind of pull that together. How do I pull that together? That's a little bit of magic here. So this is the next layer. This is the next step from just the raw pattern of light. Now the idea is that we have created this sort of internal view that suggests some important structural information. So again, surfaces, the distances between the things in the image, the orientations of things, some of the depth, so where in my depth of field is the thing. And then, but it's all still from like our personal perspective. So the final step must be to create a full 3D sketch. So the idea is to use all the information from the last panel, the last step, to create an independent, sort of fully 3D visual representation of, not visual representation, representation of the objects in the world, right? So it gives this basic understanding of what's going on, what's arranged where are this person's arms and legs relative to themselves, and you can zoom into different levels here of detail. So sometimes we will keep track of fingers, sometimes we won't. The idea is we have taken this extremely, just a straight up light pattern of dots, and using simple processes like detecting the edges, we've created surfaces, and once we know the surfaces, we can get a fully independent 3D understanding of an object out of just light. So that's the steps, right? We take the input image, we get the primal sketch of just the basic, what are the edges, what aren't, where are the lines, right? A 2D sketch based on those lines to create, okay, this is a surface, this is a cylinder, this is a circle, all that, until finally we get a much more stable 3D understanding. So, if you looked at these sets of images, how might this come together? So, here is a raw input image in a very, very, very reduced form. So, okay, this might be a little bit garbled for you. If you're into history, you might recognize these patterns, right? What are we seeing here? Well, to make sense of it as the visual system might, first we would want to detect all of the edges, right? So we get the primal sketch. Okay, so we now see there are edges, right? So along the top, along what looks like probably a horizon, we have this sort of kind of craggy set of lines. But we also have all these other sets of lines somewhere within this pattern here. Then we have a 2.5D sketch. Now this is missing some important stuff like, where are the surfaces? We at least see 3 levels, right? There's some things in the foreground, midground, and background. But there's also, information here about what direction are some of these objects pointing. Looks like you might have noticed by now, it's probably tank-like, right? So its treads are one surface, and the gun is pointed off some specific direction. And then finally, the internal representation, the internal 3D model that could be handed off for understanding this is just a sketch as remembered, right? But this is the final form of this particular described process, right? So this is a fully independent, We understand that this is 2 cylinders and a stick, right? That's a decent way to describe a tank, honestly. There's more to it than that, obviously. There's more detail in the real world and also in the way that we experience them. But this is a useful kind of high-level sketch of this object. And this is supposedly the kind of thing that we can do, that we're able to abstract information from the visual world into this kind of internal model. And it, again, in real life, it would be quite rough. It's not going to be a little drawing like this. But that's the idea. So analyzing the visual system at this algorithmic level, he went through a lot of steps, right? Marr walked through a very, very detailed process of how one could get from the light patterns in the world to a 3D understanding of the objects that inhabit those light patterns. It's very top down. So he started from this very coarse description, like broad description of what's probably happening here, and then describe the algorithm based on that. So, you know, it makes sense at higher levels, and it could be realized with a lot of different specific algorithms. And that brings us to implementation. So finally, we get to the implementation layer. And even Marr himself didn't dig particularly deep into this level of analysis. In theory, and in practice, we've seen quite often, neural populations do this fairly well. It's easy to conceive of neurons, at least in the way that they behave, that can do this. They could say, hey, these parts are bright, this part is not bright, that's a zero crossing, I'm going to use this. And in fact, spoiler is that the visual system does that constantly. In fact, it does that primarily. It splits the world up into these zero crossings. But that's nothing to say that there's not other ways to do this, right? And in fact, the implementation, an interesting thing about this multiple levels discussion is that this algorithm, it works in humans, but it can also work in machines, right? Machine vision does this. That's what is said to be multiply realizable. So machines right in your pocket can do things like this. They can create a 3D model just based on 2D visual information available. They're not very good, these ones, at least the ones I'm showing, although they're getting better every day, right? So something in your system, in your phone, is able to do all these same kinds of steps to say, hey, this light and this light next to each other imply this about this surface implies this, and it's able to create a 3D model, right? A 3D model that you can then do all kinds of stuff with in your brain or in a computer. So, Marr's model of vision. The idea is that we need some kind of system that converts images, 2D images, into 3D representations. Based on the medicine, based on the science, we know that this must be happening, right? So he then specifies this algorithmic level of how do you get from an image to a 3D representation? Let me show you the steps. And he specifies some. He was right on the money with some of these ideas, and I'd say he's a little further off with others, but he's getting it right? Getting it mostly right for the time. At the implementation level, he doesn't talk about this model at that level so much. Could be done many ways, right? A machine or a human brain could come in and do these things. So, what's the take home from Marr? Marr created the 3 levels of information processing model, levels of analysis model. And he used it to model an important cognitive system, 3D vision, in a top-down way, better specified at the higher levels than at the lower, right? But on top of just like demonstrating that it works in this one capacity, I think the really important thing to understand about the 3-level model, about how to understand levels of analysis, right, is that this gives a way to zoom in and out. It gives us a language, it gives us a sort of a bridge between higher level and lower level processes that is very stable, very useful. It's a good lens to view any given process at. And it enables this movement up and down, saying, I may want to understand how an entire process that I'm looking at actually fits into a higher level of explanation. So bottom up explanations. I may understand a lot about my current process and want to explore how it fits into things above it. Or I might want to know, given my current process, I want to ask questions about how the individual components of that process work on their own. That would be a top-down question. Say, I know how this thing works. That's what Marr did here, right? He said, I know that we must be able to get a 3D model out of a 2D shape. How does that work? I will specify at this level, and I will dig deeper. So, more important than just like knowing exactly that computational layer and implementation layer, it's more that these are relative terms. The implementation of one thing might be the computation of another, right? Those who study neurobiology think the cell of a neuron is not just an implementation component of a higher level process, it is its own very fascinating and powerful phenomenon, a process that needs to be understood. So, carrying all this forward, this levels of analysis approach is powerful for understanding information processing in general, right? There might always be more levels above, more levels below, but the idea is that there are multiple levels and we can always think more broadly or more narrowly about what we're currently looking at. We could think about the turtle, we could think about the turtle's organs, or we could think about the turtle's environment. These are all valid and they're all important for understanding each other level. So, final thought. One can think of most any working system at multiple levels of analysis. Think of any one complex system, for example, appliances, vehicles, equipment, services, and examine it at the computational, algorithmic, and implementational levels. All right. Thanks. Take care.